Hi, my name is Jose Luis and welcome to another video where this is going to be an example video where I'm going to be doing a lot of numerical sequences using repetition, using for loops and using conditional statements sometimes. And it's part of a general playlist of learning computer programming using the C# programming language. Okay, so if you're here, you either came from watching all those videos on the playlist or maybe YouTube or some algorithm just landed you here. But just so you know, this is a continuation, it's part of a whole curriculum where I'm trying to explain computer programming from scratch using C#, and you just got to the video where we just learned how to do iteration, and I'm just gonna indulge in doing like a bunch of numerical series to practice for loops because I believe it's something that it needs a little bit of muscle before continuing to learn more about computer programming. So I have a list of numerical series that I want to do together with you. And the first one, we're going to start by the beginning, which is usually a good place to start. I'm going to just print out the first 10 digits from 0 to 9. Okay, so what is going to be the first 10 digits? That's going to be, I'm going to start a for loop where I'm going to start with the first number. So I'm going to declare an integer I, for example, which I'm going to initialize to 0 because I want to start from 0 and then go all the way to 9. Then if I want to print the first 10 numbers, then I will have to be less than 10 for this for loop to keep iterating. And then I'm going to increase this value in units of 1. And therefore, as I do that, I'm going to say console write line, and then I'm going to print the value of I. All right. If I run this code, you can see that, yes, indeed, I am printing right now the first 10 digits of so this is like basically the most canonical for loop that you can think of. And instead of adding comments, I'm actually just going to, I'm just going to do this, okay? And then I'm going to just add an empty line here so that as we start drawing sequences, things start to look a bit more orderly, okay? All right, so I have that. So how about we try the first 10 negative numbers, all right? How does that look like? Well, first 10 negative digits. In order to do that, I'm going to have to rewrite my for loop. And then what I will want to do is, the list is probably going to look like 0, -1, -2, -3, -4, right? Or it could also look like -9, -8, but I think it makes more sense to do it in descending order. So because I want to start with 0, this is going to be very similar. I'm going to say int I equals 0. I, in this case, because it's going to be descending, what I want to do is, as it's going to be 0, -1, -2, I want to keep going as long as that number is greater than -10. All right? So that's going to be I is greater than -10. And then the list is going to be decreasing. So every time I'm going to take the value of I and I'm going to decrease it by 1 unit. So that's going to be I minus minus. And then as I do this, I'm going to print this to the console, and you can see that here I can see my first 10 negative numbers. All right, are we good so far? Okay, I'm going to substitute digits by numbers. I just find it a bit more clean. And also, I want to remind you of something. We haven't really seen this yet in this video series that we're doing, but I can declare these two variables with the same name, with the name I, because since I am declaring them inside of the for loop, the scope of this variable, so the lifetime, the expectancy, the life expectancy of this variable is just within this block, the block of the for loop. And what happens is that after the for loop finishes, that variable I stops existing. So because it was in the scope of this block. All right, I will explain more about scopes farther down. But what that means is that since at this point in the life of the program, at this point, I doesn't exist anymore, that's why I can declare again another variable called I within this second for loop. And I will be able to do that anytime with any other of the for loops. All right, so just a quick clarification. Now, I'm going to now create another list, and this is going to be the first 10 square numbers. And what is a square number? A square number is a number that comes from multiplying an integer by itself. Or basically, it's the sequence of the first 10 digits whose square root is a perfect integer number. So those are going to be 0, 1, 4, 9, 25, 36, 49, and I'm getting a little lost right now, but you get my point, all right? So what am I going to do? I could say int I equals 0, right? And then I could say, well, but what am I using I for? Is it actually I? Is that going to be the value of the squares? So think about this. You don't really, when you declare the variable of I, the variable of I for a for loop, you don't really need to use that I as the actual value that you're hoping to achieve. You can use multiples of that value. You can use you can use like combinations of that value, etc. And since what I want to do is to find the first 10 square numbers, what I can do is I can generate the first 10 simple numbers and then square each one of those, and that's what I can output to the console. So what I'm going to do is I'm going to create a for loop that goes over this first simple 10 digits. So I is equal to 0, I is less than 10, and I plus plus, just like the very first sequence here. But then what I'm going to print is not going to be I, it's going to be I times itself. That's as simple as that. So I'm going to execute this, and you're going to see that I'm getting here the first 10 square numbers. Again, my point with this being, if you are generating sequences of numbers, you don't really always need to generate that exact sequence by manipulating the parameters of the for loop. You can generate that sequence by creating a series of numbers with for loop and then finding a way of using combinations of that number or permutations of that number with some other number to generate that list that you're looking at, that you're looking for. All right? All good so far? Okay, so what do I have now? I have on my list, for example, that we can say, let's try the first 10 even numbers. All right? How would that work? So the first 10 even numbers are numbers that are multiples of 2. So that's going to be 0, 2, 4, 6, 8, whatever. So there's two ways. There are multiple ways that I can go about that. So for example, one way would be I equals 0. I is less than, for example, 20, right? And then I increments in units of 2. Okay? So I am just creating the first 10 even numbers right away by manipulating the parameters of the for loop. So this gives me the first 10 even numbers. So it's from 0 to 18. Okay? So that could be a way to go. Now, but there are multiple ways of doing this. I'm actually going to comment this out, and I'm going to say, well, I can also just generate the first simple 10 numbers. So I is less than 10 and I plus plus. And then what I can print to the console is that number multiplied by 2, right? Just like I did before. So I can just do this, and the first 10 even numbers, I also get this result. All right? How does this sound? Or maybe for this particular case, it's kind of an overkill, but what I could do is, well, if I'm not sure, if it was a bit more complicated, then perhaps what I'm going to do right now makes a bit more sense. But you could also say, this is a very complicated operation. I don't really know what even numbers are, so I'm just going to sample, like, I don't know, 1,000 numbers. I'm going to find the first 10 that are even, which I'm going to do with using some kind of rule. And then once I'm done with those numbers, then I'm going to stop calculating this. So something that you can do is, for example, you can say, I'm going to sample the first 100 numbers, all of them. okay? And I'm going to say, and so from I starts at 0, I is less than 100, and at increments of 1 unit. And then what I'm going to do is I'm going to check if that number is even. So I'm going to say if I is even, and wait for a second. How do we know that a number is even? Well, a very simple way of doing that is by using the Modulo Operator, and you can go back on my list. I have a video only about the Modular Operator, and we know that if we divide any integer number by 2, and if the integer remainder of that division is 0, then that number is going to be even. All right? So that's what the Modulo Operator does. So if I modulo 2, if the result of dividing I by 2, if the remainder part of that division is equal to 0, remember we use double equals when we compare things together. Simple equals is assignment. So if this number modulo 2 equals 0, that means that the number is even. So I'm going to print this to the console. All right? I'm going to do this. And then you can see that, oh, I printed but I didn't print the first 10 even numbers. I printed all the way to 100. So I printed way too many, right? So what can I do here? Well, maybe what I can do is I can say, I'm going to create a variable where I'm going to keep track of how many numbers I have found already. So say I'm going to name it found, and I'm going to initialize it to 0. Okay? So now every time I find a number that is odd, I'm going to print it to the console. Then I'm going to take the value of found, whatever that was, and I'm going to increase it by 1 unit. All right? And just so that we can see it very clearly on the console, I'm just going to print here a message that says something like found already this many even numbers. Okay, I will remove this later on. Okay, so let me see how that works. You can see after each one of these even numbers, I'm printing this message, oh, I already found 39, 40, 41, whatever, blah, blah, blah. Okay? So what I can do now is I can say, I am keeping track with this variable outside of the for loop. I'm keeping track of how many numbers I have inside of how many numbers I have found that are even already. Okay? So what I'm going to do now then is I'm going to say, if the number of variables that I have found is greater or equal to the value of 10, then I don't want to keep checking anymore. I want to stop. So something that I can do is I can just say, just break. Just stop the for loop, stop executing, stop everything. All right? And let's see if this works. So if I do this, you can see that indeed I get the first 10 even numbers, even though this for loop has probably run 20 times before it was called to break, because I just found more than 10 numbers. All right? For such a simple problem, even numbers, probably this situation is an overkill. All right? We can be a bit more smarter with simple for loops, but I think this situation, by having like a variable that we use to keep track of things that are happening inside of the for loops, we have one condition checking the even numbers. Inside of that we have another condition, whether if we have found too many numbers and we need to stop. I hope that this example starts giving you an idea of how, with these basic building blocks that we have learned so far, by combining them, we can start achieving like much more complexity and much more richness in our capacity to do to write algorithms. Okay, so this could be another way to go about this. All right. So which one am I going to choose? I don't know. I'm probably going to stick with this one. It feels a bit more elegant, a bit more clear. All right. Similarly, what about the first 10 odd numbers? Sorry, the first 10 odd numbers. How does that work? I wish I had students here so that I could ask them. So what do the first 10 odd numbers look like? Well, it's going to be something very similar to what I did before. It's going to be I starts, what I did before for even numbers is that I started at 0, it was less than 20, and I increased by 2 units. So it's probably going to be something very similar, but in this case, you can see that I cannot start with 0, because 0 is an even number. So what I need to do is I need to start with the first odd number. So that's going to be the number 1. And then I can see that by increasing in units of 2, I'm going to get 1, I'm going to get 3, I'm going to get 5, etc., etc. So I'm going to run this code, and then you can see that indeed I can start now with 1, 3, 5, 7, blah, 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 etc., etc. Okay? So that looks good. Another way I could do this is, again, simple as copying. I'm going to copy from the previous one here. I'm going to say the first 10 odd numbers. And in this case, what I can do is I can just sample the first 10 numbers, all right? 0, 1, 2, 3, 4. And then how can I use those numbers to generate the first 10 even numbers? Sorry, odd numbers. When I was using this technique for even numbers, what I said is I'm just going to take the value of 0, 1, 2, 3, 4 and multiply it by 2, right? But in this case, it's not going to work if I do that because it's going to give me 0, 2, 4, blah, blah, blah. What do you think you could add here or you could change so that this gave me, instead of 0, 2, 4, 6, 8, it gave me 1, 3, 5, 7. I'm going to give you 3 seconds. And some people in the chat are giving me the right answer right now. Thank you very much. Yes, so you can just take 0, 2, 4, and if you add 1 unit to all those numbers, then you get all those even numbers. Sorry, all those odd numbers. So it's just as simple as taking 2 times the value of that number and adding the value of 1. So you can see here 1, 3, 5, 7, 9, 11, etc., etc., using this technique. And last but not least, what if I wanted to copy this technique here, the one that I said it was overcomplicated, right? The one that relied on using found and using integer, blah, blah, blah. Well, the code is the exact same code. It's just that I have to change just one number. And what do you think I would need to change from this algorithm in order to get the first 10 odd numbers? I'm going to give you another 3 seconds. Well, in this for loop, I'm checking the first 100 numbers, and I'm checking with this line of code, I'm checking if they're even. And if they are even, that's how I print them to the console, and then I add 1 unit to how many I have found, etc., etc. So what I need to do is I need to change this, and instead of checking if they're even, I need to check if they are odd. So what do I change here? Well, we said that the modulo operator means that if I divide the number by 2, what is the integer remainder of that operation? So in the case of 6 over 2, 2 fits inside of the number 6 3 times, and it fits perfectly, so the remainder is 0, and that's why 6 is an even number. But what about the number 7? The number 7, the number 2 fits inside of the number 7 also 3 times, but there is 1 unit left, and that's why 7 is an odd number. So what I can do is I can say, well, I can say if the remainder of that division, aka the modulo, is equal to 1. Or also, somebody's saying in the chat right now, if the remainder of that operation is not equal to 0, right? Both work in this case, then this number is going to be odd. So if I run this code now, you can see that the first 10 odd numbers, I can find them with this technique as well. All right. Which one of the methods do I like better or worse? Well, I still think this one is a bit of an overkill for such a simple scenario, but I thought it was very pedagogical, so I'm going to keep this, and we're also going to use this technique for more for loops down the road. So I kind of like this one for some reason. I don't know, I find it elegant, the first 10 numbers and then multiplying them by 2 and then adding 1. I kind of like this, so I'm just going to go for this one, but for no particular reason really. Okay. Some people, maybe pure computer scientists, would argue that this one takes like a few, is a bit more optimized because it takes a few less multiplications to perform. I don't know about that, but at this level, I don't think those level of resources really matter at this point. Wonderful. Let's continue and let's do some more for loops. So for example, something that is a very fun exercise is to plot on the console the multiplication table of a particular number. Okay. So for example, I'm going to copy paste here one of these modules, one of these blocks of code. Okay. And I'm going to say here the multiplication table of number what? What number? Actually, let's be a little more programmatic. Instead of hard coding that number, let's use a variable to define which number is going to be. So that's going to be, for example, multiplication value. And that's going to be, for example, let's say it's going to be number 7. So then here, when I print the message, I'm going to use string interpolation. So I'm going to add a dollar symbol here and open and close curly brackets. And this is going to be mult value. And so I'm going to plot here the multiplication table for number whatever. Okay. Now, what is the next thing that I'm going to do? When I write the multiplication table, what I want to do is I want to say the number times 0 equals whatever. The number times 1 equals whatever. The number times 2 equals whatever. So what I want to do is I want to be able to sample the first 10 values of the multiplication table and print a nice message to the console with that table. All right. So probably what I would want to do is I will want to have an iteration where I start with the number 0, or maybe I want to start with number 1. Maybe I want to start with number 1 because, I mean, typically every number multiplied by 0 is 0. And then this is going to be less or equal than number 10 or less than 11, whatever you want to make it. And then here, what I can do is I can print a nice interpolated message that says, for example, I'm going to print a dollar here and double quotes, and I'm going to say the value, so mult value times whatever we are, so the number I, so that's going to be 1, 2, 3, 4, whatever, has to be equal to those two numbers multiplied. And if you remember from the string interpolation video, what I can do is within the square brackets, I can actually, within the curly brackets, I can actually not just have one variable. I can have like a full expression, like a full statement there. So I can say, give me the multiplication value times I. And this is what we're going to plot on the screen. So if I run this code, you can see that all the way down here, I get 7 times 1 is 7, 7 times 2 is 14, 7 times 3, 21, blah, blah, blah. And again, why not? Let's just start with 0 and go all the way up to 10. I kind of like it better. It feels more rounded up, you know? And you know, my tiny OCD feels a bit happier with that. So 7 times 0 all the way to 7 times 10. And we can do that now for any single number that we can think of. So now this can be this crazy number, I don't know. But the code is so programmatic and so clean that that we get this. And actually, surprisingly, this is a very interesting example. This number is so large as an integer that very soon, when we start multiplying it with 3, it actually overflows the capacity of how large an integer number can be, and therefore it starts looping back into negative values, like here. So this is not a don't freak out about that. This is a problem with memory allocations and memory tables and how big numbers can be. So actually, if we want to make things work, something that we can do, I believe, is we can just change the type of this variable. Instead of being integer, we can make it long. And long is just an integer that has way more capacity than a normal integer. So if we do that, then I believe that we will get the actual multiplication table of this crazy number that I just typed. All right. So, so yeah, that was actually fun. All right. So, but I'm just going to bring it back to an integer just for the sake of, and then just make the number a little smaller so that we stay within boundaries. Okay. All right. So that's it for the multiplication table of a number. Now, another thing that we can do is we can just write a geometric series. And what does that mean? That means a series in which the numbers don't have a linear growth. They don't have the same step between them, but they grow exponentially. All right? And how can we do that? So for example, something that I can do is, instead of working with integers, as I described in the video, I can also use floats or doubles as numbers with decimal part that I can manipulate and that I can work with while iterating with my for loop. It's just that it's very typical to use integers because very, very often we want to relate the for loop to how many times we have looped over the for loop, but that's not necessary. That doesn't necessarily have to be the case. All right. So for example, if I initialize a double value that is going to start at 1, for example, it's going to be b, and I'm going to start it at 1. Okay. Then b has to be less than 100, and every time for each iteration, instead of adding 1 or subtracting 1, what I'm going to do is I'm going to multiply this value by 1.5 times, so that the number starts growing, but it starts growing increasingly large over time. So what I'm going to do is I'm going to multiply this by 1.5, and then I'm just going to simply print it to the console as is. If I do that, you can see that the number starts growing, 1, 1.5, 2.25, 3, blah, 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 and then it becomes larger, much faster than it used to here. All right? And the fact that these numbers like form this really beautiful pyramid is kind of coincidental because of the 1.3, I think. If this was 1.68 or something like that, it would probably not be so beautiful. Yeah, it's a little messier here now. But we could make this much larger if we multiply it by 1.21, so like a very small number. You see, the series will be much larger because it takes more time for the number to grow. Okay, so let's say we just keep it at 1.5 as a geometric series. Okay, and similarly, we can write a very similar series where we say, let's say that this is going to be an ascending geometric series, and this is going to be an asymptotic geometric series. It's going to be asymptotic because I'm going to start with the value of 1. I'm going to request that this value is greater than 0, and then what I'm going to do is instead of making it grow, I'm going to make it shrink. So every time I'm going to multiply the value by half. So I'm going to do plus equals 0.5. Okay? And then I'm going to run this code. This code is a little weird for the reasons that you're going to see right now. If I do this and I print it, you can see that, ooh, what is happening here? That was a little strange. Let me scroll up a little bit. Ooh, so we have, what is this, about 200 values? So look at what's happening. The value starts at 1, becomes 0.5, 0.25, 0.125, blah, blah, blah. But the number starts getting very, very small. Like very, very small, like 0.000. And at some point, it gets so small that it switches to exponential notation. Exponential notation is basically, this is the mantissa, is basically the significant part of the number. And then this is how many zeros to the left we need to move the comma so that this number is actually a real number. So what this number means is that it's this number with this comma moved 5 digits to the left, or with 4 extra zeros in front of it. All right? And see what happens. This is 5 zeros, 6 zeros, 7 zeros, 8 zeros, and very soon, the more we start decreasing, we start getting like 155 zeros, 255 zeros, 324 zeros. So this number is literally 4.95 with 323 zeros in front of it. It's like a really, really small, like a tiny number, you know? What happens is that this sequence that I just created, basically it's ill-defined. It's ill-defined because it's asymptotic, because a number that I keep making it half and half and half and half and half is like the Achilles and the tortoise paradox. That number will never, ever, ever reach zero. And even more importantly, that number will never, ever, ever become less than zero. Because a number that I keep making half will always, always have some kind of value over zero. The problem is that the series actually ends up finishing. It ends up finishing because double numbers have a lot of precision, but they have a limit to that precision. And the precision cannot be any more than roughly what you just saw. A number with 320 plus zeros in front of it. So a number with 320 plus decimal parts. All right? And that's why when it reaches the limit, it basically just snaps to zero, which is not what it should be in a purely mathematical environment. But it just snaps to zero due to the limited precision that computers inherently have. All right? So if I were to fix this so that it wasn't an asymptotic geometric series, but it actually ended at some point, I could just specify here some very small number. So long as this is greater than 0.01, then keep going down. Or, right? And then the number just becomes smaller, smaller, smaller. All right? Or maybe I can add a couple zeros here, and to get a few more values that are right there, you see? But theoretically, again, this series could never reach the value of zero, just by making every number half of the previous one. Just doesn't work. All right? What are we doing next? Okay, so we've done a lot of for loops with integers. We've done a couple of for loops with double values so that you can see that we don't always have to increase by 1 or decrease by 1. But we can also use for loops not to print stuff on the screen. We can use for loops to generate sequences of other things. So for example, let's say that we wanted to use a for loop. Let's say that we wanted to generate an alphabet in a programmatic way. I wanted to generate a sequence of all the letters in the alphabet, one after the other. How could I go about that? Yeah, I could just say string alphabet is going to be equal to A, B, C, D, E, F, G, blah, 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 but like I'm already tired. I'm already tired of doing this. And there's got to be a better way. There's got to be like a programmatic way of doing this, right? And this is also prone to errors. Maybe I'm a human and I forget a letter, or maybe I'm using an alphabet that I don't control, or that is not my natural one. So this is probably not a good way to go. So the way to go about this is that I can use a for loop to iterate over all the letters and then add that letter to the alphabet that we are creating. So how are we going to do this? The way we're going to do this is we're going to first initialize a string variable. We're going to call this the alphabet, and this is going to start empty. All right? And then one at a time with a for loop, what we're going to do is we're going to generate a new letter, and then we're going to generate a new letter, and then we're going to stitch that letter to the string that we already have. Okay, so we're going to concatenate that letter to that string that we are using as the alphabet. So how is that going to work? How many letters are in the alphabet? 24? I forget. The Spanish alphabet has like a few more letters, I think. Anyway, so let's say that I start a let me say this. I start a for loop that starts with 0, I is going to be less than 24, and I is going to grow in increments of 1. Okay? And then what I need to do is on every one of these cycles to the alphabet string, I need to add a new letter. But wait, how do I generate those letters? This doesn't work, because if I add I and then I print here to the console, if I print alphabet and I print a white line, then what I'm going to get is not that, but it's basically like all the numbers one after the other. So that doesn't work. So how can I use these 24 numbers to fetch a letter? Oh. So we're going to use a very simple trick. Let me fire up a browser, and what I'm going to do is I'm going to pull up the ASCII table. So I don't know if you're familiar with this. I spoke about this on my Harvard computational design lectures, etc. But basically, a very early representation of a very early code to represent letters through numbers was the ASCII table. And this ASCII table, in this ASCII table, you can see that basically every character, here denoted in red, every character has representations in octal, in hex, and in decimal numbers. Which means that, for example, in uppercase A, in decimal numbers, is the number 65. And lowercase a, in decimal notation, is the number 97. So if, let's say that I want to do an alphabet with uppercase letters, I know that A is going to be the number 65. So what I can do is I can say, I can take the number 65 and convert it to a letter that then I can switch into that I can concatenate into the string. So what I can do is I can say, let me take the number 65, which is the letter uppercase A, and then use casting. We already recorded a video where we speak about conversions between different types, and it just so happens that when you convert simple numerical integers to characters, by default by default it uses ASCII representation. Well, it is not exactly like that, but it uses UTF-16, but the first 255 numbers of UTF-16 correspond to the ASCII table. It's a long story, but bottom line, 65 corresponds to the uppercase letter A, and 97 corresponds to lowercase a. So if I do this, you can see that the number 65 gets converted to the character A 24 times, all right? But this is not the alphabet. This is just A repeated 24 times, right? So what I need to do is I need to use these numbers here, and so every loop, what I'm going to do is I would like to concatenate into the string. I would like to concatenate number 65 plus 0 plus 1 plus 2 plus 3, so that I do A, B, C, D, E, F, G, blah, 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 blah. And A, B, C, D, blah, 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 and it looks like I'm missing a letter, so probably it's 25 here. All right, oh no, still it's 26 letters, apparently. And now we got it, all right? A, B, C, D, F, G, blah, 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 all the way down to C. If I wanted to make this lowercase, I could just switch this to the number 97, and then I would have the letters lowercase, okay? And then I'm going to pimp this up a little bit, the alphabet, okay? And just for the sake of flavor, something that I could do is I can print how the series alphabet keeps growing over time. So something that I can do is I can just, okay, I'm going to create an interpolated here, interpolated string where I'm going to print the value of I and then semicolon, no, a colon, and then the value of alphabet. And this way, we can see how for the numbers 0, 1, 2, 3, the alphabet string keeps growing in a pyramid kind of way. You see? 0, 1, 2, 3, how the letters keep growing all the way until we get the full alphabet. How does this sound? Hmm? Is this cool? Are we learning anything today? Okay, so this idea, the idea of using a for loop, in combination with a variable that I have defined outside of the for loop, and we will see very soon why that is important due to the rules of variable scoping. We will, using a variable that we have declared outside, and then inside of the for loop, start working and adding and modifying that variable is a really, really common technique. It's so common that it's very useful for a lot of things. So for example, let's say that I wanted to calculate the addition of the first 10 numbers, aka 0, what is the result of adding 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus blah, blah, blah. What is the result of that? Okay? So let's say that I'm going to create here the addition of the first 10 numbers. So I can create a for loop here and say I'm going to iterate starting at 0, and it's going to be less than 10, and it's going to be I++, and then I'm going to write here that value. Okay? But because what I want is, I want one number, and I want to add all these values that I'm generating, 0, 1, 2, 3, to that number, and then print the result, then this is not exactly what I want. What I would like to do is I would like to create a variable called, for example, mass addition, and this, I'm going to start it at 0, and then for every iteration of the for loop, what I'm going to do is I'm going to say mass addition should be equal to whatever the value was of mass addition was before, plus this new index, this new value that I just generated. Okay? Or if we like shortcuts, then this that I just wrote is exactly the same as writing plus equals. All right? So mass addition, add the value of I. And then here afterwards, I can just say, I can just print mass addition and the result. So what that gives me is that the addition of the first 10 numbers is the number 25. All right? All right, so let's keep going. And then what about, this is going to be a good one. What about the Fibonacci sequence? Huh? Do we know what the Fibonacci sequence is? Who knows? The Fibonacci sequence is very simple. I'm just going to write it here. The Fibonacci sequence is 1, 1, 2, 3, 5, 8, and then it's 13, and then it's 21, and then it's 34. 34. Who knows where is this coming from? The Fibonacci sequence is a sequence where we start with 2 number ones, and then every number after that is the addition of the 2 previous numbers. So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 3 plus 2, 8 is 5 plus 3, etc., etc. You get it, right? So what we need to do, let's say that we want to create, for example, we want to print out the first 10 or the first 12 Fibonacci sequence values, okay? The way we're going to do this is that just like we had just like we are using external variables outside of the for loop to, just like we're going to use external variables outside of the for loop to keep track of something that we're calculating, we can use that similar technique to also keep track of certain values that we need to keep in memory, all right? And so that we can, for our calculations, for our present calculation. What that means is that we're going to create a for loop where we're going to go over a bunch of numbers. We're going to look at the two previous ones that we generated. We're going to use those two to generate the new number in the sequence. We're going to print that to the console, and then once we have that, we're going to update those two last numbers to the new two last numbers that we have calculated. All right? So what does that look like? It looks like something like this. Let's say that I say previous number first is going to be equal to 1, and previous number 2 is going to be equal to also the number 1, because we have to start with those two values. All right, we're going to print them to the console. So I'm going to say, let's print this one, and then let's print previous 2. And then what we're going to do is now we're going to create a for loop where we're going to iterate 10 times. So I equals 0, I is less than 10, I plus plus. And then in this, in this side of this for loop, we're going to create a new variable, which is going to be the sum of both previous values. So previous 1 and previous 2. Okay? And we're going to print this to the console. We're going to print here sum. All right? Now, if I run this code, you can see that, yes, we get, oops, what have I done? We get 1, we get the sum of the two previous ones. So 1 and 1 is 2. But then after that, we keep getting the value of 2, right? So this is not really working. And it's not working because every for loop, every iteration of the for loop, we're calculating the sum of previous 1 and previous 2, so the two previous values. But there is nowhere in the code where we're changing previous 1 and previous 2. Through the whole life of the for loop, previous 1 and previous 2 maintain those values of 1 and 1. So that's why we keep constantly printing to the console 2, 2, 2, 2, 2. All right? So what we need to do is, after we calculate it and we print it, what we need to do is we need to update the values of the two previous values that we will use in the next iteration of the for loop. All right? What does that mean? What it means is, whatever value I had here in previous 2, I probably need to pass it on to previous 1, and then previous 1 is forgotten. And then the value of sum, that value of the calculation, should become the value of previous 2. So that in the next cycle, this value had moved 1 unit, and this value is the sum of the previous cycle that we just calculated, right? So how are we going to do this? Well, it's going to be pretty easy. So previous 1, whatever it was before, I don't care anymore. That's going to disappear because now it needs to be the value of previous 2. So previous 2 moves on one position back into the line. And then previous 2 is now going to be equal to the value of sum, so that for the next iteration, I have the two latest numbers that I've calculated in this series. All right? So I think at this point, we are ready to give it a try, and it should probably work. Is that correct? 1, 2, 3, 5, 8, 13, 21, 34. I think it works. The Fibonacci sequence. All right. How cool is that? I'm so nerdy sometimes. I love it. Okay, and now, last but not least, we're going to do perhaps, well, not perhaps, clearly what I think is the most advanced or the most hacky series of these videos yet, in case you hadn't had enough, which is going to be, we're going to calculate for the first 100 values, 100 numbers, we're going to calculate which ones of those are prime numbers, okay? And for that, we need to remember what a prime number is. A prime number is an integer, is a natural number that cannot be divided wholly by any other number below it. Or in another way, it cannot be the product of any other two numbers and of any other integer numbers. All right? Which means that basically, if you have a prime number, you cannot divide that number by any other natural number below it and get a number without decimal part. All right? So those are the ways that we can think of prime numbers. So what we'll have to do in order to figure this out is create a for loop, go over the first 100 numbers, and then figure out if for that number, if dividing it by all the numbers that are below it, if any of those divisions gives me an integer division, gives me a division that has no remainder, that has no decimal part. Okay? And if that happens, then, and if there is a number that gives me no decimal part, then that number is not a prime. But if I can't find any, then that is a good number. It's a prime number. All right? So how am I going to do that? Well, first of all, I'm going to write here a header. So prime numbers. All right? And what I'm going to do is I'm going to create a for loop that is going to go over the first 100 numbers. Or the first 10 numbers, whatever. Let's do 100. I think it's more fun. But in this particular case, I'm going to start by the number 2, because we cannot really start by the number 1. The number 1 is prime, but it's obviously, there's no number under it, so you cannot really divide it by 0. That's actually not possible. It's an indetermination, right? So what I'm going to do is I'm going to start by I equals 2. I has to be less than 100 and I plus plus. All right? As I do that, what I'm going to do here is that now for each one of these numbers, 2, 3, 4, 5, 6, whatever, what I need to do is I need to take that number and divide it by all the numbers below it. And again, all the numbers below it except for the number 0 and the number 1, because every number is divisible by number 1. Okay? So what can I do for that? Well, in this case, we're actually going to have to apply the technique of nested loops. So for here, for all the 100 numbers, for each one of them, I'm going to have to create another for loop where I'm going to try to divide that number by all the numbers below it. So this is going to be a bit trickier. So let me show you how this works. So here I'm going to create a for loop. I'm going to declare another variable. This one is going to be called j, all right? And what I'm going to do is that j is going to be the number that I'm going to be dividing I by. So if I is 6, for example, I want to start dividing j by, by 5, 4, 3, 2, etc. Or I want to start by 2, 3, 4, whatever, in whichever order you want, okay? So j is going to be the number that I'm going to use to start dividing. So let me say that this is going to start at 2, all right? And I'm going to start dividing all the way up. So I'm going to say, if j is, so if I is the number 6, for example, then I need to divide 6 by numbers that go from 2 to 5, all right? Which that means that j is going to have always to be equal, sorry, it's going to have to be less than the value of I, all right? So the numbers that I'm going to use as divisors are going to start at 2 and are going to go all the way to the value of I minus 1, okay? And then here I'm going to say j is going to grow in units of 1, okay? Now, so what I'm going to try to check here is dividing I over j and seeing if the remainder of that operation is a whole number, is a number with no decimal part, all right? So what I could do is I could actually try to do the real division. So I could like cast I, j to doubles, make that division and see if the decimal part is perfectly 0. But that is a little complicated, and since these two numbers are already integers, there's actually a better way of doing that. The better way of doing that is that I can say if I modulo j equals 0, then that means that the division of a over j doesn't have any remainder, so it's a perfect division of two natural numbers, which means that that number is not going to be prime. Okay? So if that number is not going to be prime, then what I can do is I can already break from my calculations, because for that number I have already figured out that it's just not possible, that it's not a prime number. Okay? So we are getting close. So let's see if this works, or let's see if it gives me like an infinite, some kind of, no, it looks like it's working well. All right, so that is working well. Now, now what I need to do is, if no number was found that was equal to 0, that the modulo was equal to 0, then what I need to do is I need to print that to the console. So something that I can do, a technique that is very popular, is to use what's called a flag. All right? A flag is nothing, it's like a nickname for a technique that involves creating a Boolean variable that I can use to keep in memory, to remind myself if the number that I'm currently calculating is a prime value. So for each one of the I values that I'm checking, I'm going to create a new Boolean variable. So that I'm going to do here inside, just right above the second for loop. I'm going to create a variable called is prime, and I'm going to initialize this to the value of true. So until proven guilty, I'm going to think that all numbers are prime. However, if I find that at some point dividing I over j gives me no integer remainder, so it's a perfect division, then this number is actually proven guilty. And then what I can do is I can change that variable is prime, I can make it false. All right? So again, I'm creating a variable to remind myself if I is prime, I initialize it to true, all right? And then I'm going to check all the other values below I if they do have a perfect division. And if there is a perfect division, then the number is not going to be prime. I don't need to keep checking any more of those values, so that's why I break from my for loop. And then after that, after I have created the value and I have checked against those divisions, at this point in the code, I should have a value for is prime, which is either true or false, depending on those calculations. If at this point the value of is prime is still true, it's because no other number here was found that gave me a perfect division. So what I can say is, if is prime equals true, if the value of is prime is still true, then I can safely say, let's print the value of I to the console, because I know that this is going to be prime. And let's see if this works. Yoo-hoo! It looks like it may have worked. So let's take a quick 2, 3, 5, 7, 11, 13, 19. Whoa! These numbers look prime to me. I don't know what you think, but they look pretty prime to me. All right. There's no number that ends in 2 or 4 or, there's clearly a number divisible by 2, by 5. Those are very easy to spot. So probably it's working. All right. And you can see how we have made use of nested loops for the sake of performing a computation that is purely numerical, which I find is pretty nice and pretty elegant, I think. These things are a bit difficult to explain verbally. I should have probably used some diagrams, but whatever. I guess that's what I just did. Okay, so this is going to be the end of this exercise where we have reviewed for loops, and I have explained a bunch of other examples of how to use for loops, perhaps in non-standard ways. But again, trust me on this one, probably like 50%, 60% of the for loops that you're going to write are going to be as simple as that, as like int I equals 0 is less than whatever number and I++. That's like literally the bread and butter of writing for loops, okay? However, I wanted to expose you to some other examples and some other techniques, and hopefully like open up your brain a little bit about how we can combine everything that we have learned so far to make more complicated, more interesting algorithms. Like for example, the prime number one, which I thought was a really interesting example. Okay, so thank you very much for being here. If you like what you just saw, please subscribe, hit the notification button, and keep watching this series where I'm trying to break down the secrets of how to write code using, in this case, C#. Okay, see you in the next video.